Last time we talked about some limits that ended up either being infinity or negative infinity. Something like, for example, well, maybe, sorry, let me make some things here. Today is the 24th. Yes. So for example, last time we were doing some problems, kind of like maybe say the limit as x approaches 5 from the right of 2x plus 1 times x minus 7 over x squared minus 5. And there's a couple of different ways to go about doing a problem. Oh, sorry, x squared minus 25. Apologies. So the way I like to do this is just to plug it in. So if I just plug in the 5, look what happens. On top, I get 10 plus 1, so 11 times 5 minus 7, which is negative 2, divided by 25 minus 25. Now, I think it's not too terrible just to say, I can see that since x is on the right side of 5, then x squared is going to be a little bit bigger than 25. And this denominator is going to be slightly positive. I know Alameda likes to write the positive sign out in front of the 0. I prefer to write it as a superscript up here. Overall, my sign is negative on top, positive on the bottom. So overall, this is a negative thing, and it's going to be going to negative infinity. However, this is not the only way to do it. Some people, I think Alameda specifically, when he sees a limit like this, likes to factor it as much as possible. So I'm going to rewrite it as 2x plus 1 times x minus 7 divided by x minus 5 times x plus 5. And then we're going to look at the number line. And on the number line, the only time a function can change from positive to negative is either by going through 0, aka an x-intercept, or by having a vertical asymptote. So here, the only places where we're possibly going to change signs are where either the numerator is equal to 0 at x equal to positive 7, or x equal to negative 1/2, or at the vertical asymptote where x is equal to positive 5 and x is equal to negative 5. So those are the only places we can change signs. And then we can kind of look at the overall sign like this. So if x is bigger than 7, then this factor is positive, this factor is positive, this factor is positive, this factor is positive. So the whole thing is positive over there, bigger than 7. But then between 5 and 7, say we picked 6, that part's positive, that part's negative, that part's positive, that part's positive. So overall, we have a positive times a negative over a positive times a positive. The whole sign is negative. And we could do more, right? We could keep doing this. But to answer the question that's being asked, since we're approaching 5 from the right-hand side, and we see that the function is negative on the right-hand side of 5, we have to end up getting negative infinity. Negative because we said it was negative, infinity because we're dividing by 0. So that's another way you can kind of attempt to do a problem like this. Not my way of doing it, but it's a way that definitely works. I will also point out, you could do this for the rest of the thing. So between negative 1/2 and 5, I'm thinking of 0, positive, negative, negative, positive. So the overall sign is positive. Fix this here. Yep. And then between negative 5 and negative 1/2, like if x is negative 3, negative, 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 positive. So the whole thing is negative. And finally, if x is less than negative 5, like negative 6, negative, 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 negative. So the whole thing's positive. So if we were going to kind of graph this, we would say, okay, there's some sort of vertical asymptote at negative 5, some sort of vertical asymptote at positive 5, and the graph is, let me draw it down here. The graph is positive, then it's negative, then it crosses through at negative 1/2, and then it goes up positive like that, and then negative again, crosses at 7, and goes positive. What we can see as we approach x equal to 5 from the right-hand side, oh yeah, the function goes down, 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 down to -5. So really you can do whatever you like as long as it works. My way works, his way works, other ways work as well. So let me give you one to try on your own. And you can attempt to get this problem in whatever way you prefer. So try the following. The limit as x approaches 3 from the left-hand side of x minus 7 times x plus 1 divided by, sure, 3 minus x. 3 minus x cubed. So try that. It should be some sort of infinity. Your job is to figure out which kind. All right, let's take a look. So doing it this way of making the sign chart for the function, I can see that if x is larger than 7, I'm going to pick a number like 8. I have a positive factor, and the negative factor cubed is still negative. So it's a positive times a positive divided by a negative, which means it's negative overall. Between 3 and 7, like at 4, negative factor, negative factor. So overall, it's positive. Over on the other side of 3, like plugging in 0, negative, positive, positive. So the whole thing is negative. How do I know, by the way? It's based on how many negatives there are multiplied together, right? If you have an odd number of negative things multiplied together, it's going to be negative. If you have an even number of negative things multiplied together, it's going to be positive. And the positive parts don't really make a difference. They just leave it alone, essentially. And finally, over here on the other side of -1, we have, say, -2, a negative factor, and a positive factor overall. That's negative times a negative over a positive, so the whole thing is positive. So now if we look at the part we're actually interested in, which is approaching 3 from the left-hand side, we can see that on the left side of 3, the whole thing is going to be negative. So we're getting negative infinity. Or if you want to do it more like I like to do it, I'm actually going to plug in 3 to x minus 7 times x plus 1 divided by 3 minus x squared. Sorry, 3 minus x cubed, apologies. And get -4 times +4 divided by 3 minus 3 is 0. But since this number is a little bit less than 3, 3 minus a number smaller than itself is going to be a little bit positive. And then it's cubed, so it's still positive. So we have a negative times a positive over a positive. The whole thing is negative overall. And since we're dividing by 0, it's got to be negative infinity. Either way is totally fine. Unless your professor says you have to do it a certain way, right? Either way is fine in the context of they both work, but if your instructor says do it this way, then you should do it the way they tell you. Which usually most people aren't like that. Like as long as you're doing correct math and the things you're writing down are not like coming from nowhere, usually people are pretty okay with doing it the right way, whichever way. There are some exceptions. Hopefully they're making. So questions about either of these things before we do other things? Yeah. So one more time. The -4 here. So what I'm doing, like I usually do with a limit, the first thing I almost always do is I just plug in the 3. So what I'm actually doing is I'm plugging in the 3 here and I'm getting 3 minus 7 times 3 plus 1 divided by 3 minus 3 cubed, which is then becoming, well, 3 minus 7 is -4. 3 plus 1 is +4. And the bottom is a 0, but it's a slightly positive number. That's how I'm getting that. Yeah. No, it didn't. So the denominator was positive because the inside part was positive. In this case, it actually wouldn't have mattered if the power was 3 or the power was 2, because the inside part being positive, a positive number squared or a positive number times itself, same thing, is still positive. A positive number cubed or a positive number times a positive number times a positive number is still positive. So whenever the inside part's positive, doesn't matter what the power is. The reason the inside part's positive is because the number we're plugging in, I'm writing down 3, but I'm thinking a number less than 3, like 2, 2.5, 2.9. And if I think about plugging in 2.9, I can see that 3 minus 2.9 is slightly positive. On the other side, if we had asked for this, I will say this sign chart is actually especially useful if they're asking for more than one side. So if I then asked for the limit as x approaches 3 from the right-hand side of the same thing, x minus 7 times x plus 1 divided by 3 minus x cubed. Well, I know I'm still dividing by 0, so I know it's going to be infinity or negative infinity. And looking at the sign chart up here, well, the right-hand side of my 3 is going to be positive overall. So I'm pretty sure it's going to be positive. But if I do it the way I like to do it, plugging in 3, I'm going to get 3 minus 4 on top, 3 plus times 3 plus 1, divided by 3 minus a number a little bit bigger than 3. Thank you. Can you tell that was a 7? You were right. Thank you. 3 minus 7 times 3 plus 1, yes. And then on the bottom I have 3 minus 3, but that 3 is a little bigger than 3. So 3 minus a number bigger than itself is going to be negative, right? It's like 3 minus 3.1 or 3 minus 4, slightly negative. So there on top, we've got a -4 times a +4 divided by a negative number cubed. And when you raise a negative number to an odd power, it retains its negativeness. Or as I like to say, odd powers and also odd roots keep the sign. So if you have a negative number to the third power, it's still going to be negative. If you have the cube root of a negative number, it's still going to be negative. Same thing is true if it's positive. Cube root of a positive number is positive number cubed is still positive. So odd powers and odd roots always keep whether the thing is positive or negative. Even powers do not, right? A number squared is always going to be positive, whether or not the input was negative or positive. So here we've got a negative divided by a negative, so that's going to equal positive infinity. And that makes sense, right? If we look at our sign chart, oh yeah, coming from the right-hand side of 3, we're definitely going positive. So we have an asymptote that looks like on the left-hand side of 3 going down like that, on the right-hand side of 3 going up like that. I should say we have a vertical asymptote where that's what's happening, which we could, I suppose, draw. At x equal to 3, we know that from the right-hand side, we're going up to infinity. From the left-hand side, we're going down to negative infinity. Sorry, I can't quite see that. So these types of limits where you are starting, so again, I would always recommend, even if you want to draw the sign chart thing, plug it in first. Observe that you're getting not 0 divided by 0. And we know that when we have not 0 divided by 0, the limit's either going to be infinity or negative infinity. Or if it's a double-sided limit and the two sides are doing opposite things, it could not exist. So I will just say one more thing here. If they asked you to talk about the limit as x approaches 3 of the same thing, we would have to just say that this limit didn't exist because the right-hand side and left-hand side are not doing the same thing. They're not both going to the same type of infinity. So this limit does not exist because the left-hand side and the right-hand side aren't doing the same thing. Or approaching, and I don't want to say that. Going in the same direction. Yes?
In order to find that, you have to.
Right, exactly. So what I'm going to clarify. In order to find that, you have to find the left-hand limit and the right-hand limit, which, yes, we write with a plus superscript and a minus superscript, but I really want you to say in your head, the left-hand limit is when you see that minus in the superscript, the right-hand limit is when you see that plus in the superscript. Other questions?
Like, I know when it's a constant on infinity, it's 0.
Mm-hmm.
In this case.
Well, I would argue I do have a constant over infinity. Because when I plug in x going to 3, my a constant over 0. Sorry, I think I said a constant over infinity. But really what I'm getting here, which I didn't write out, is I'm getting negative 16 on the top divided by a negative number that's very small on the bottom. And the negative divided by a negative gives me positive, and then since I'm dividing by something really, really, really small, my fraction blows up and gets really big. So yeah, so as long as the numerator, even though there's x's in the top, when you plug in whenever x is approaching, as long as the numerator isn't 0 and the denominator is 0, it's going to be one of these three things: infinity, negative infinity, or does not exist. Those are the only choices. Okay. Other questions about other things? Yeah.
You can run over a few domain and range problems.
Yes. Putting things in the right place here. Domain and range. Yeah, okay, sure. So if I were going to ask a domain question on an exam, I would maybe ask it in the following way. Find the domain of the following functions. We'll do maybe 2 or 3 examples here. First one, f of x equal to the square root of x minus 3 cubed times x plus 1 squared times x plus 3. That seems decent-ish. Okay. So very similarly to what we were just doing, the way we're going to deal with the domain here, well, I should back up. I'm getting a little ahead of myself. Before I even start thinking about a number line, I should think about, okay, I have a square root. And for square roots, the argument or the insides has to be greater than or equal to 0. So the first thing I'm going to write down here before anything else is x minus 3 cubed times x plus 1 squared times x plus 3 greater than or equal to 0. And that really should be everyone's first step. So that the person grading your exam knows that you know to make that first step, right? Even if you know to do it in your head, but you write something else, you should write this. And then I would do the same number line thing we just did for the sign of the function. I want to know when this thing is positive. So I'm going to draw on the number line all the places it can change signs, aka all the zeros or solutions and all the asymptotes, the vertical asymptotes. This thing doesn't have any vertical asymptotes. It only has values that makes it equal to 0. Notably positive 3, negative 1, and negative 3. And then we do the same sort of thing. We say, okay, well, if I pick a number larger than 3, like 4, that part's positive, that part's positive, that part's positive. I usually don't write positive times positive times positive, but you can to say that the overall thing is positive there. And then if we pick a number between negative 1 and 3, I would always pick 0 if 0 is an option. 0 minus 3 is negative. A negative number cubed is still negative. 0 plus 1 is positive. 0 plus 3 is positive. So I have a negative times a positive times a positive. So that's going to be negative there. Now, a couple things about this. Doing this can be tedious, right? If you're plugging in the number, checking the signs, plugging it in. Another way to see what's happening is to observe the even or oddness of the power on each factor. So 3 came from the x minus 3 to the third power, which is an odd power, and the sign changed. -1, as we'll see in a second, came from a factor with an even power, and we will see that the sign is going to stay the same. So when the powers are odd, the sign stays the sign changes, and when the powers are even, the sign stays the same. Well, let's check just to be sure. Between -3 and -1, we got -2. -2 minus 3 is negative. Cubed is still negative. -2 plus 1 is negative, but a negative number squared is positive. Oh, look, that's the thing that would have changed, but it didn't because it's raised to an even power. And then the -2 plus 3 is still positive. So we have a negative times a positive times a positive, which is still negative. So the sign didn't change when we crossed from the right side of -1 to the left side of -1. And finally, crossing -3, the power, well, -3 came from the factor x plus 3, which is raised to the first power. So we expect the sign to change. And it does. If we look here, we have a negative number cubed is still negative, a negative number squared is positive, and a negative number to the first is still negative. So negative times the positive times negative is positive. So now we have to answer the question, right? Making the sign chart isn't the finished product. We have to say, okay, well, where is this product greater than or equal to 0? So here are the greater than parts, the plus parts, and here are the equal to parts, the 3 and the -1 and the -3. So my domain here is going to be everything from -infinity up to -3 with a bracket, because I want to include the -3. And -1 is on its own little island here between a negative part and the negative part, but we still need to keep the -1, right? That -1 is a valid part of the domain. So we say union the squiggly lines that include just -1. Those are called braces. And then also everything from 3 to infinity, including 3. So yes, if you have one point all by itself between a sea of things you don't want, it gets those squiggly line braces around it, because that's the set containing just that single number. Yeah.
Why do we want the -1?
Because it's a valid point to plug in. If I plug in -1, what do I get? Let's see, I get the square root of -1 minus 3, so -4 cubed, -1 plus 1, which is -0 squared, and -1 plus 3. What's -4 cubed times 0 squared times -1 plus 3? Everyone, 0, right? If you multiply by 0 at some point, you're done. The whole thing is 0. So we have the square root of 0. What's the square root of 0? 0. 0 is a valid input. I should say, I apologize. -1 is a valid input because it makes the whole inside equal to 0, and we are allowed and can take the square root of 0. It's equal to 0. So -1 is good, but anything next to -1 is not. If you try plugging in like -0.999, this whole thing is going to be a negative times a positive times a positive, which is going to be negative overall. And we cannot take the square root of a negative number. So yeah, it's kind of weird when you get those isolated ones by themselves, but that's what we do. Let's look at another example. Let me think for a second here. Sure. Let's say that's not a great question for range. The next one, that's what I was trying to think of. The next one to be something that was good to take for the range. Sure, let's find a little classic. So let's say our function is g of x equal to 3x minus 2 over 5x plus 10. And here we're going to find the domain and the range. And for this one, the domain should be relatively straightforward. For the domain, well, here, the only thing we have to worry about, there aren't any square roots, there aren't any logarithms, but there is potential division by 0. So we have to make sure that we exclude any value of x that makes the denominator equal to 0. In other words, exclude the values where 5x plus 10 is equal to 0. Solve for x. 5x equals -10, x equals -2. So here our domain is every real number except for -2. So everything from negative infinity to -2, parentheses, union, parentheses, -2 to infinity. Everything else is valid, right? You can plug in any other number for x and get some top number divided by some bottom number. It's not 0 on the bottom. I would also mention, just because we're looking, this function would certainly have a vertical asymptote at x equal to -2. And you could be asked about the limit as x approaches -2 from the left and the limit as x approaches -2 from the right. But we're not going to ask that right. We're today going to talk about the range. So there's, in my opinion, two ways to find the range. One way is to graph the thing. This is not what we're going to do here. Graphing this, it's not super obvious what you're missing from the range if you graph it and you're not careful about graphing it. So typically to find the range, we're going to find the domain of the inverse function. Meaning we have to find the inverse function. So to find g inverse, we're going to first start with our original function, but I'm going to write it with a y instead of a g of x. So we're going to start with y equals to 3x minus 2 over 5x plus 10. We're going to switch x and y to get x equal to 3y minus 2 over 5y plus 10. And now we're going to solve for y, which is the step that actually takes some doing. So solving for y, if you've ever got a fraction, the first step is to get rid of the fraction, or in other words, to multiply by both sides by the denominator. So we're going to have 5y plus 10 times x equal to, we should just write 3y minus 2, but if you prefer, we can write 3y minus 2 divided by 5y plus 10 times 5y plus 10. And on the right-hand side, the 5y plus 10s divided to 1. That's why we multiply by that in the first place. On the left-hand side, we're going to distribute the x to each term. We've got 5y times x plus 10x equal to 3y minus 2. We're trying to solve for y. It means all the y's have to get grouped on one side and all the not y's have to get grouped together on the other side. So I'm going to put the y's on the left-hand side. I've got 5yx minus 3y. Put all the other stuff on the other side. So it's going to be a negative 10x minus 2. Finally, factor out a y from the left-hand side. So factoring out a y, we're left with 5x minus 3 equal to negative 10x minus 2. And then finally, divide both sides by 5x minus 3 to get y equal to negative 10x minus 2 over 5x minus 3. So our inverse function is negative 10x minus 2 over 5x minus 3. And the domain of the inverse function, well, just like the original function, we want to exclude where the denominator could be equal to 0. So we want to make sure that we exclude 5x minus 3 equal to 0, which is 5x equal to 3, or x equal to 3/5. So the domain of G inverse is going to be everything from negative infinity to 3/5, excluding 3/5, union 3/5, exclusive to infinity. And that is equal to the domain of G inverse, which is equal to the range of the original function g of x. Kind of a lot of work. So that said, someone else could say, give you the picture of a function and then ask you to find the range by looking at all the y values you're getting. In fact, yeah, question.
Fix the 5x. Oh, because it's the.
Because that's my denominator, right? I can't divide by 0. So let me point out a different type of range question. And this is on the first page of Alameda's practice exam. If I can pick it up. So it looks like this. It says, Consider the following graph of a function y equal to f of x. Based on this graph, write down the range of the function. We're going to write down the domain and the range because I think that's more fun. So first, the domain. So I'll point out this graph doesn't go left of the y-axis. So x isn't negative. We're starting at almost 0. So we don't actually even get to 0 for x. So our domain is starting at 0. And I suppose that's not a great question, really, that I have to say here. We're not missing a value there. We're not missing a value there. We're not missing a value there. And nothing is numbered on the x-axis, which is why this is not a good question. And then we keep going further to the right. So our domain here is everything from 0 to infinity. We're not missing any x inputs. The range, on the other hand, is the more interesting question for sure. So let's see. When I think about range, I think about y values, and I really think about going from the bottom to the top. So at the very lowest, this goes down, down, down to negative infinity. And then it goes up, up, up to a y value of -3, but I don't actually get -3, right? There's a circle, there's an open hole there. So my range is starting with a low of negative infinity up to the first breakpoint, which is at -3, and we're excluding -3. And then we're going to pick it back up at what's the next y value we have. Yeah, if we keep going up, we get -1 is the next kind of lowest thing we have, and that's included. It's going to be a bracket -1 up to all the way to 2, but with the parentheses, because we're not including 2. We keep going up, 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 up. Looks like 4 is the next value we get, and we do get 4. So it's a bracket 4 up to a 5, also included with the bracket. We don't have anything between y equals 5 and y equals 7, but we do start back at 7. But we're not including 7, we're excluding 7 because there's a hole there. So that's how we find the range based on this graph. It's looking for every y value you get, and we're trying to not write down the ones we don't get. So I'll point out we are missing, right? We're missing everything between -1 and 3. Right? We don't get, sorry, -3. We don't get -3. We do get -1. We're missing everything between 2 inclusive and 4 exclusive. We're missing all that. We're missing everything between 5 exclusive and 7 inclusive. Those are all the things we're missing, right? We don't have anything between -3 and -1. We don't have anything between 2 and 4. We don't have anything between 5 and 7. Yeah. I mean, it looks the same as mine.
No, for the domain. You put 0 in,
Mhm.
and I just. rewrote
So
it.
that would not be the domain. That's the range.
Oh, okay.
So the domain, so very kind of generically, the range is all the possible y values, and the domain is all the possible
Oh, wait,
x values. Right? If we look here, we're getting all the x values that are bigger than 0. Right? We're not missing any x values.
no, yeah, I think I just reread it wrong.
Sure. So in my mind, those are the two types of range questions you can ask. Either they can give you a function and ask you to find the range by finding the inverse. Let me give you one more actually. Or they can give you a graph. Let me give you one more example. Is your question about this or something else? Okay. Let me give you one more example of a range question, and then we will move. Whoops. Dropping papers everywhere. And then we'll move on. So here is one more function. I don't want to write this in red. Ugh, terrible. Who writes in red? F of x equal to, sure, let's make it x squared minus 4x plus 5. Find the range. This is a very specific example. What kind of graph does this function have? Start to the P. The parabola. And we know a parabola either has a bottom if it opens upwards or a top if it opens downwards. AKA, if we can find the vertex of this parabola, we can find one of the boundaries of the range. We know this parabola looks, I don't know what it looks like exactly, but I definitely know it opens upwards. I really like to find its vertex. There's a couple ways of finding the vertex. You could say that the x coordinate of the vertex is negative 4 divided by 2 times 1. It's more generically negative b over 2a is equal to the x coordinate of your vertex. So that's going to be positive 4 over 2, which is 2. So the x coordinate of my vertex is 2. And the y coordinate, if I plug in that 2 to my function, f of 2 is 2 squared minus 4 times 2 plus 5, which is 4 minus 8 plus 5, which is 1. So what's the lowest y value we get? 1. And every other y value is higher. So here the range would be everything from 1 inclusive to infinity. But nothing lower than 1. Right? That function could never equal 0 or negative 1 or negative 3 or anything like that. It seems less likely that you'd be asked to do this, but not impossible. I would say if I were to ask this question, I'd probably actually write it in the following way. I'd probably write it more like f of x is equal to x minus 2 squared plus 1. This is the alternate way of writing this function in the vertex form. Here, the vertex is more obviously seen to be, oh yeah, my vertex, the x value is 2, the y value is 1. And then we know it opens upwards, so we know that y equals 1 is the lowest value, and then the y values just get larger and larger. But I will point out, this is the same function as this. It's just written in a different way. All right. What was your question?
You do a question on sequences.
Sequences, sure. So there's lots of things to say about sequences. I'm guessing you mean something more about like maybe finding the formula for the sequence.
Yeah.
Sure. So let's say our sequence terms look like this. A sub. Now I think I'm gonna do this. Sure. A sub 2 is equal to 8 thirds. A sub 3 is equal to 12 negative 12 ninths. A sub 4 is equal to positive 16 27ths. A sub 5 is equal to negative 20 81st, so on and so on. We want to find the generic formula for A sub n. Okay. So when you have a fractional type sequence, which a lot of them are, but not all of them, but if I see a fraction, I'm usually thinking of the numerator and the denominator wholly separately. Like I'm really just gonna say, well, let's look at the numerator and see if we can find a sequence for that. So for the numerator part, and I should say, let me back that up even one step. I'm also thinking if it's alternating, I'm gonna think of that as a third separate part. So there's gonna be 3 pieces we're gonna put together. The numerator sequence 8, 12, 16, 20, the denominator sequence 3, 9, 27, 81, and the alternating part positive, negative, positive, negative. So first for the numerator. Yeah, for the numerator, sure. So I have 8, 12, 16, 20. What's the next term? 24 and then 28. We obviously see what the pattern is that we're adding 4 each time. So I know that my formula for the numerator is something like, I'm gonna call it a different letter name because I don't want to call it A sub n since I already used it. So maybe I'm thinking of A sub n as like a B sub n over C sub n times a negative 1 to the something. So I'm thinking that my B sub n for the numerator is going to be, well, you said you're adding 4 every time. If you're adding the same amount every time, that's the amount that gets multiplied by n. So it's 4 times n. Did I do it? Oh man, I did make it too easy. Oh well. Usually you have to add something onto this. But since we're starting at A sub 2, if I plug in n equal to 2, I exactly get 4 times 2 is 8. And then if I plug in n equal to 3, I get 4 times 3 equals 12. So in this case, my B sub n is just 4n. Should have made it harder. Oh well, I didn't mean to make it not hard, but sometimes it happens that way. Let's look at what's happening with the denominator. So my denominator terms are 3, 9, 27, 81. And to me, it looks like we are multiplying by 3 each time. So here's what I'll say. If you're adding the same thing each time, you get that amount multiplied by n. If you're multiplying by the same thing each time, you get that multiplication factor raised to the nth power. So that means our bottom part is going to look something like 3 to the n. The problem is 3 to the n is too big. If I plug in n equals 2, my c sub 2 is 3 squared, which is 9. My c sub 3 is 3 cubed, which is 27. It's like I'm a multiple of 3 too big. So you could either write it as divided by 3 if you prefer, because that'll fix it. Or if you like, you can be, oh, 3 is really 3 to the 1, and 3 to the n divided by 3 to the 1 is going to be equal to 3 to the n minus 1, which is probably the preferred way to write it. So let's think about it. If we plug in n equals 2, right, because that, again, my first subscript is 2. If n equals 2, 2 minus 1 is 1, and 3 to the 1 is 3. So c sub 2 now correctly equals 3 to the 2 minus 1, which is 3. And c sub 3 is 3 to the 3 minus 1, which is 3 squared, which is 9. 3, 9, the next one will be 27, the next one will be 81. So my sequence is looking something like a sub n equal to, let's see, my top part is 4 times n. My bottom part is 3 to the n minus 1. And then I have to make it alternate. So I need to multiply by a negative 1 to the n or a negative 1 to the n plus 1. Here's what I suggest. Always start with n. And then check. If you plug in the first value of n, which in this case is n equal to 2, do you get the right sign? And in this case, we do, right? If I plug in n equal to 2, I get negative 1 squared, which is positive 1. And I'm starting with a positive 1 times 8 over 3. And if we switch the signs, if we made it negative 8/3, positive 12/9, negative 16/27, positive 28 over 81. If I did this again and said, okay, well, I'm going to check it now. If I plug in negative 1 squared, I get a positive 8/3, and I want a negative 8/3. Then I change it to the other option, which is negative 1 to the n plus 1. Because then if you plug in n equal to 2, you get negative 1 to the 2 plus 1, which is negative 1 to an odd power, which is going to stay negative 1. So whenever it's alternating, you're always going to have either a negative 1 to the n or negative 1 to the n plus 1. And you just have to really just pick this one first, check to see if it's right, and if not, turn it into that one. Do we do another one? Okay. Try and not make it too terrible here. So let's say our terms are the following. So we'll start with a sub 1 equal to, think for a minute here. Sure. Let's say that's going to be 4 over 7. A sub 2 is going to be 9 over 12. Negative 9 over 12. A sub 3 is going to be positive 16 over 17. A sub 4 is going to be negative 25 over 22. And your job is twofold. First, take a guess at what a sub 5 is going to be, and then try to find a formula for a sub n. And I'm going to think of a sub n as negative 1 to the something times a top sequence divided by a bottom sequence. So I would say work with the bottom sequence part first. See if you can figure out what's going on in the bottom. And just to make sure everyone can see this, that's a 4 over 7. That's a negative 9 over 12. That's a positive 16 over 17. The negative 25 over 22. All right, let's see what we've got. So I always try to deal with just with the easiest part first. And I think the easiest part's the bottom of the fraction, because I can see that for the bottom part, how much are we increasing by each time? It's like 5. So if I had to guess the next term, the bottom part of the next term would be 22 plus 5, which is 27. And I'm pretty sure that my formula for the bottom part is going to be 5 times n plus something. Or maybe minus something. I still usually write plus though, and this is write plus a negative thing. So if I'm starting at n equal to 1, then if I plug in 1 for n, 5 times 1 is 5, but I wanted 7, so it should be 5n plus 2. If I had done a different thing, if I had said that this was if I had started at A2 instead of A1, then my 5 times 2 would be 10, and I'd have to subtract 3 to get 7. So sometimes it changes based on where you're starting. So that's the formula for the bottom part. For the top part, 4, 9, 16, 25, we should hopefully recognize all as what kinds of numbers? 4 is 2 squared, 9 is 3 squared, 16 is 4 squared, 25 is 5 squared. So that's 2 to the second, 3 to the second, 4 to the second, 5 to the second, and my next term should be 6 squared, which is 36. And then comparing that to the index, well, when my index is 1, I get 2 squared. When my index is 2, I get 3 squared. When my index is 3, I get 4 squared. My index is 4, I get 5 squared. It looks like the number getting squared is exactly 1 greater than the subscript number. So it looks like my b sub n here is going to be n plus 1 squared. If n is 1, I get 1 plus 1, which is 2 squared. Oh yeah, if n is 2, I get 2 plus 1, which is 3 squared, and so on. And then finally, which of these is it going to be? Well, my a sub 1 should be positive. If I plug in 1 here, negative 1 to the 1 is negative. If I plug in 1 here, negative 1 to the 1 plus 1 is positive. So it's going to be this one, because negative 1 to the 1 plus 1 is positive 1. So putting these 3 pieces together, my actual formula should be negative 1 to the n plus 1 times my b sub n, which is n plus 1 squared, over my c sub n, which is 5n plus 2. Let me show you one more thing here. So what if instead they'd said something like, something terrible, like they gave you a sub, the same sequence numbers, but they called the first one a sub 4 and the second one a sub 5. And obviously the third one is a sub 6, which is 16 over 17. And my next one is a sub 7, which is negative 25 over 22. I still have the same pieces going on, but they're going to get altered just a little bit. So for the bottom part, which is still 7, 12, 17, 22, my bottom part is still going to be some Cn equal to 5 times n plus something. But now, when I plug in my first n, which is 4, C sub 4 should equal 5 times 4 plus something that's going to make it equal to 7. And 20 plus negative 13 is going to be 7. So that's what needs to go there, is a negative 13. It's still the same idea, right? It's still 5n, but the amount we're adjusting it by, instead of adding 2 to get to 7, we're subtracting 13 to get 7 because we're starting at a different n starting place. Similarly, my squares here, 2 squared, 3 squared, 4 squared, 5 squared. Well, I'm getting 2 squared when n is equal to 4. I'm getting 3 squared when n is equal to 5. So it looks like the number getting squared is, instead of being 1 bigger than n, it's 2 less than n. So it looks like my formula for the top part here is going to be not n plus 1 squared, but n minus 2 squared. Because we're starting at n equal to 4. And 4 minus 2 is 2, and 2 squared gives you the 4 we're starting with. And then 5 minus 2 is 3, and 3 squared gives you the 9. And n equal to 6 is going to give you 6 minus 2, which is 4, and 4 squared is 16. So it's still the same overall kind of formula. It's just you're shifting it a different direction by a different amount. Is that a hand for a question or just, yeah?
For the bottom part,
Uh-huh.
you just put, 5 brackets and -2 and then.
Oh yeah, you could totally, I would never have thought to do it that way, and that's 100% correct. Yes, you could totally smartly write it as 5 times, is n minus 2? I think I went with n minus 3 actually. I guess it depends on how you want to do it. Because we're starting n equal to 4, right? So, sorry, what did you say you wanted to do it as? 5 times. Okay. And then I would still need a minus 3 out here.
Oh, no, my bad. Yeah, -3.
Yeah. So you can do it, but so the answer is there's really a lot of ways to do this. But I like your idea. She's essentially saying she wants to start at n equal to 1 is kind of the idea. So what she's saying is I'm gonna make it 5 times. Well, if I do n minus 3, that's gonna start me at 5 times 1. And then I'm still gonna add 2 to get back to 7. It's smart. I like that. I'm trying to squeeze this in here. I'm totally running out of room. It's awful. But I'll point out this thing that's written here is exactly the same as that. Because 5 times n minus 3 is 5n minus 15. If you add 2, negative 15 plus 2 is negative 15. So both ways totally work and get you to the same spot. So here, our overall formula would be that a sub n is equal to, my top is n minus 2 squared. My denominator is 5 times n minus 3 plus 2. Or if you prefer, it could be just 5n minus 13. But I think this is a smarter way of doing it. And then my negative 1 to the something, well, if I start with negative 1 to the n and I plug in n equal to my starting value, which is 4, negative 1 to the 4th is positive, and I want to start positive, so we're good to go. So it can be a little tricky, but it is very doable. So the things I would encourage you to remember, there's basically 3 types of patterns we see. Either you're increasing by the same amount of time or decreasing by the same amount of time. So like you're adding 5 every time, you're adding 4 every time, whatever. Or you're multiplying by the same number each time, like multiplying by 2 each time, or multiplying by 3 each time, or multiplying by 4 each time. That's when you get something to the nth power. Or you got something like 4, 9, and 16, 25, where you see squares. That's kind of the third thing. It's just kind of its own thing. Those are the 3 patterns I would try to be aware of when I was looking at a sequence. All right. Other questions? Sure. Somewhere there. Yeah. Yes. Yes. Great. I was hoping to do more continuity. So continuity, which we started talking about last time, but didn't quite finish up. Let's see, where'd you go? Also, I should just do a quick check-in. Has anyone talked about, let me be very specific here. Has anyone mentioned the limit as x approaches 0 of sine of x over x? I know someone did the limit as x goes to infinity of sine of x over x, but does anyone talk about this? I'm hoping the answer is no. Okay, looks okay. So if again, I'm keeping an eye on what's going on in your classes, but if this comes up, please let me know so that I can talk about it in class. Because it is kind of a weird limit, but it is a useful limit. So that's related. Okay, continuity. So where's my example? Yeah, let's see. So let's say we had the following function. F of x is equal to cosine of x plus 2 when x is less than 0, and it's equal to -1 when x is bigger than or equal to 0 and less than or equal to 2. and is equal to, sure, 3 minus x squared when x is bigger than 2. And so, like I said last time, I'll say it again. Usually with these questions, the question is like, where is this function continuous? And you can either really the question is that where is it not continuous? What I want to point out is this function is guaranteed to be continuous almost everywhere. It's certainly continuous everywhere less than 0 because cosine is a continuous function. It looks like this. It's certainly continuous between 0 and 2 because if you're equal to -1, you're just a horizontal line. And it's certainly continuous when x is bigger than 2 because 3 minus x squared is just a polynomial and every polynomial is continuous on its domain. So the only questions about continuity are, is this function continuous when we change from the left side of 0 to the right side of 0? And is this function continuous when we change from the left side of 2 to the right side of 2? Or in other words, is it continuous at 0? And is it continuous at 2? So let's talk about 0 first. And when I'm thinking about continuity, I'm always looking to test the 3 things. First, is it defined? Most of the time it will be because it's kind of boring if it's not. Like, it's like, well, yeah, it's not continuous, it's not defined, we're done. So usually functions are going to be defined as 0. So question 1, what's f of 0? Well, which piece of the function am I using? The top, the middle, or the bottom? We're using the middle, right? Because that's where x is equal to 0. So f of 0 is -1. I'm not really plugging in the 0, right? Because it's just a constant function. I'm just looking to see where x is 0 and then saying, okay, well, that's my function. Since the function is always equal to -1 for any value between 0 and 2, it's just -1. The second part, which is usually the part that causes some consternation, is what about the limit as x approaches 0? And often, although not always, for piecewise functions, that involves looking at both of the one-sided limits. So the limit as x approaches 0 from the right-hand side of f of x is the limit as x approaches 0 from the right-hand side. I'm going to use the piece of the function that's on the right-hand side of 0, which is, again, the middle piece. So we're going to have the limit as x approaches 0 of -1. And good news, the limit of a constant is just equal to the constant. You're just saying, oh yeah, we're -1 the whole time. What are we getting closer and closer to? Well, -1, the thing we've already been the whole time. On the other side, if we look at the limit as x approaches 0 from the left-hand side of f of x, now we have to use the piece of the function where x is less than 0. That's going to be the top part. So it's the limit as x approaches 0 from the left of cosine of x plus 2. Most of the time, not all the time, for these these piecewise functions, most of the limits you have to end up taking when they're left or right-sided, usually you can take them just by plugging in when x is approaching. Most of the time that just works. It's not like some weird 0 over 0 thing that you've seen in other limits. That's the case here. We're just going to get cosine of 0 plus 2, which is equal to 1 plus 2, which is 3. But that's not the same as -1, which means the limit as x approaches 0 of f of x does not exist. And once one of the things fails to exist, the whole thing is discontinuous at that point. So I would say that f of x is not continuous at x equal to 0 because the limit doesn't exist. The left-hand side and the right-hand side aren't meeting up. There's a jump from a value of -1 to a value of +3.
Earlier when we were talking about just the expression of there. Did you say both?
So here's what I said. I said cosine itself is continuous where it's defined. So cosine x of 2 is continuous all the way from -infinity up to 0. And certainly the middle piece is continuous where it's defined from 0 to 2. But where so technically I should say the middle piece is continuous from 0 excluding 0 to 2. It's still defined there, but it might not be continuous there because the right side of the function and the left side aren't necessarily matching. So each of these pieces individually are continuous on their own domains, except for the endpoints. And then they might be not matching up with the endpoints.
So if all of those had like the including zero, so like X.
Then we wouldn't have a function. Because if the top part included 0, then the function would define it to be equal to both +3 and -1 when we set x equal to 0. Let me show, so the easiest way to really see this is to see the graph. So if we look at the graph of this, cosine of x plus 2 looks like the following. And we're exclusive. So it looks like that. It's open circle there. And then got a period of pi. It looks vaguely like this. And it continues on that way. And then f of x equal to -1. That's just the horizontal line at -1 from 0 to 2. And it certainly is defined to be equal to -1 there. But we definitely don't have continuity. Because even though the function is defined at 0 to be equal to -1, the function is approaching the value of +3 from the left-hand side of 0, and it's approaching the value of -1 from the right-hand side of 0. And we can certainly see visually, oh yeah, that doesn't look continuous, right? There's this jump from, oh, we're getting close to 3, and then boom, down to -1. So that's why we have this continuity. Each function on their own is continuous. I should say it's continuous on the domain that it's on, excluding the endpoints. We don't know for sure it's continuous at the endpoints until we test. Because when you change from one piece to the next piece to the next piece, you might get jumps like this that give you discontinuities. So let's look at the other point in question, x equal to 2. And again, we go through the same 3 steps. Well, we didn't even go through the third step here. The third step would have been to have checked if the function value was equal to the limit value. But since the limit value didn't exist, we didn't even get to ask that third question. We're already done. For x equals 2, same sort of deal. The first part, f of 2 is equal to -1. The second part, since we know we're gonna have to do the left and right hand limit, let's just start doing the left and the right hand limit. So I almost always do the limit first for the function that's I've already used to find what the function is defined as. So the limit as x approaches 2 from the left-hand side of f of x, we'll still use the same piece of the function that I used to define f of 2. So it's limit as x approaches 2 from the left of -1. And again, the limit of a constant function is just that constant. On the other side of 2, limit as x approaches 2 from the right-hand side of f of x. Now I have to use the piece of the piecewise function where x is bigger than or equal to 2, or just bigger than 2, either way. Here x is bigger than 2, so I'm using that piece of the function 3 minus x squared. And then, just like usual, when I'm taking a limit, I try just to plug in the value x is approaching, and I'm going to get 3 minus 2 squared, which is equal to -1. So great, that means the overall limit does exist. The limit as x approaches 2 of f of x is equal to -1. And then part 3, we can say, well, great, since both the limit is equal to -1 and the function is equal to -1, they're the same value. That means we get continuity at x equal to 2. So f of x is continuous at x equal to 2 because f of 2 is equal to the limit as x approaches 2 of f of x. And graphically, what this looks like is our downward opening parabola, 3 minus x squared, would have looked like this, and then exactly hits that point right there and keeps going down like that. So there's the rest of our function. They happen to meet up at 2. I should say, they happen to meet up at the point 2 comma -1. Let's do one more concept. Yeah. Unless there's questions, are there other questions about this one? I do think it's good to write the limits down when you do this. Some people kind of like write to like, ooh, gosh, the words are really coming out. Some people like to write things like f of 2 minus is -1 and f of 2 plus is -1. You can probably get away with that, but it's not the best notation. So if you can stomach it, I certainly would encourage you to write the limits. I imagine your instructors want you to do that. If I get the paper straight here. Let's look at this next example. Yeah, I like this one. So let's say we have the following function. G of x is equal to the piecewise function x squared minus 16 over x minus 4 when x is not equal to 4 and 7 when x is equal to 4. So I'll point out the top piece, which is a rational function, the polynomial divided by another polynomial, is continuous wherever it's defined, which in this case is everywhere except for 4. So the only place we're really concerned about continuity here is it continuous for? Oh, I should back up 1 second to the previous question. So I'll just point out for the previous question, if they ask you where this function's continuous, our answer should be the interval of continuity. So this function was continuous everywhere except for at 0. So it's continuous on the interval from -infinity to 0, excluding 0, union 0 exclusive all the way to infinity. If 2 was also missing, then we would have had a 0 to 2 parentheses and then a parentheses 2 to infinity. All right, let's look at this next one. So where is g of x continuous? Well, again, this question almost always means tell me where it isn't continuous and then remove those values and everything else is your answer. So here, the only place of concern is at 4. So what's happening at 4? Well, again, our same 3 steps. G of 4 is defined, and it's defined to be 7. In this case, when we take the limit as x approaches 4 of g of x, there is no need to do a left-hand and a right-hand limit because the function is defined to be the same thing on the left side and the right side of 4. We didn't write it exactly that way because it's like you could write this, although you shouldn't. You could write this as g of x equals x squared minus 16 over x minus 4 when x is less than 4, and 7 when x is bigger equal to 4, and x squared minus 16 over x minus 4 when x is bigger than 4. But I don't need to write all that because this means the same thing. On either side of 4, the function is defined to be x squared minus 16 over x minus 4, which means the double-sided limit we can just do in one shot. We don't have to do a left side and a right side. Or they're the same. So that's going to be the limit as x approaches 4 of x squared minus 16 over x minus 4. And if we plug it in, we get 0 divided by 0. Which means we're going to reset and say, okay, well, I can probably factor. The numerator does factor as x minus 4 times x plus 4. And the x minus 4 divided by x minus 4 becomes 1. So we're left with the limit as x approaches 4 of x plus 4, which is 4 plus 4, which is 8. And here's the mistake a lot of people make. People are like, cool, the limit exists, the function is continuous. It's not true here. Right? The limit exists, great. The function exists, also great. But they're not the same, so we do not have continuity. So we would point out that g of x is not continuous at x equal to 4 because the limit as x approaches 4 of g of x, which is equal to 8, does not equal g of 4, which is equal to 7. This is the thing I see people miss the most often, is they're all super excited the limit exists, and then they're like, continuity. But no, the limit exists is necessary, but it also has to equal the function value. a very typical question someone might ask for something like this is, first of all, well, first we should finish the question, right? It didn't say where it was continuous yet. So I would say g of x is continuous on the interval including everything except for 4. So negative infinity to 4, union 4 to infinity. But then a follow-up question is often something like, what value could you change g of 4 to be equal to so that it was continuous? So they kind of write the question as, if f of x was equal to the same thing, x squared minus 16 over x minus 4, when x is not equal to 4, and c when x is equal to 4, what should we define c to be equal to so that this function is continuous everywhere? How can we define c to get continuity everywhere? And what's the answer? What should c equal? Is it 7 or 8? Let's see. When g of 4 was 7 last time, we got not continuous because the limit wasn't equal to the function value. The limit we can't really change, right? The limit's going to be equal to 8 because this piece didn't change. But we can change c to be the thing that's going to work now. We should define c to be equal to what the limit's equal to, which is 8. So to have continuity, you want the limit value, which is 8, and can't change, to equal the function value, which we now get to decide is also going to be 8. All right, let's see. Oh, I know there was one other thing I should say. So, sorry, somewhere. I feel like I should mention briefly. Raise your hand if your teacher has talked about the squeeze theorem. A few of you. Whose class are you in? Okay. Let's briefly mention the squeeze theorem. So the squeeze, also known as the sandwich theorem. And yes, I know we only have like 3 minutes. It's somewhere. I don't know where it went. Might be behind you. It might have fallen on the floor somewhere. There it is. So the squeeze theorem or the sandwich theorem is a way of evaluating the limit by saying it has to be between 2 other things. So here's a very classic example. We want to find the limit as x approaches infinity of cosine of x divided by x. But the problem is, if you look at just cosine, it does this forever and ever and ever, no matter how far to the right you go. Actually, to the right, right? We're oscillating back and forth between -1, -1, and +1. But here's what we can do. And this is usually a technique we use, especially when cosine or sine pops up and the inside of the function is just getting larger and larger and larger. So we can say cosine of x, no matter what x is between -1 and 1. And then we can divide everything or multiply everything by whatever we need to so that the middle part of this compound inequality looks like the thing we're trying to take the limit of. So we can, I would say we can divide everything by x. -1 divided by x is less than or equal to cosine of x divided by x is less than or equal to 1 divided by x. And since x is positive, which it is because x is going to infinity, there's no worry about having to change the direction of the inequality. And now what we do is we take the limit of the boundaries or the things that are bounding cosine of x divided by x. So if we take the limit as x goes to infinity of 1 over x, what do we get? What do we get? Yeah, right? Because you got 1 divided by a big number, that's going to be super duper small. And similarly, the limit as x goes to infinity of -1 over x is also going to be 0. Or actually, it's -0, which is 0. Fun fact, in case you haven't heard this before, 0 is the only number that's its own negative. -0 is equal to 0. It's also 0 is the only number that doesn't have a positive or negative assigned to it, right? It's in between the positive and negative. So we can say by the squeeze theorem, the limit of the middle part Well, since it's less than or equal to 0 and bigger than or equal to 0, the limit as x goes to infinity of cosine of x over x has to be between 0 and 0, aka it's equal to 0. And just for fun, I know it is 1:30, so if you got to go, it's totally fine. But if you look at the graph of this, you can see this kind of really nicely. So if you graph, say, y equal to 1 over x and y equal to negative 1 over x, and then y equal to cosine of x divided by x, you can see how it's trapped in between those two functions. And as you move further to the right, they're both scrunching down to 0. So the thing that's bouncing back and forth is also getting scrunched down to 0. All right, that's all I got.